I believe many design and analysis methods commonly used in industry contain three major sources of error. In the variability handling approach, these are improved through three separate steps. The first step is how we represent variability. Instead of approximating data with a normal distribution, my approach uses something called a kernel distribution. A kernel distribution follows the actual frequency distribution of the data, so it can reproduce the real shape much more accurately. Here, I generated 10,000 random samples using distributions shaped like it and B. Then I calculated the probability that the value becomes larger than mean plus standard deviation, and compared the results between normal distributions and kernel distributions. Both it and B have roughly the same mean of 5 and standard deviation of 1, but their shapes are different. These kinds of shapes are common in real design and analysis problems. Distribution A represents cases like randomly operating systems, where frequencies naturally decrease toward the right. Distribution B represents manufacturing situations where strict performance requirements reduce yield, and defective parts are removed by suppliers. The true probabilities above plus sigma in the generated data were A, 88.2%, B, 79.0% when assuming a normal distribution and calculating only from mean and standard deviation. A became 84.1%, B became 81.6%. This produced errors of 4.1% and 2.6%. When using kernel distributions instead, A became 88.4%, B became 80.1%. The errors were reduced to only 0.2% and 1.1%. Even when comparing many other datasets, standard deviation methods often produce errors of several percent to around 10%, while kernel distributions are usually within 1%. And the problem becomes even larger afterward. If product quality is guaranteed using only mean and standard deviation based on normal distribution assumptions, those errors continue to grow during later calculations and decision-making steps. As explained, the variability handling approach uses distributions that closely reproduce the real shape of actual data. In the second step, it calculates result distributions while faithfully preserving the probability information contained in those distributions. Then, in the third and final step, relationships between multiple distributions are evaluated probabilistically using distribution-based metrics. By doing this, we can achieve much more accurate decisions in many kinds of design and analysis. At the same time, it also opens the door to many new types of calculations and analysis methods.